So as I promised, I said I'd give a quick lesson with adding 3 or more vectors. So that's what we're going to cover in this lesson. There's really nothing new here. You've done everything when you added 2 vectors. This just gives us a little extra practice. It'll also remind us of a couple situations that occurred and probably give you the answer to a couple of questions that you will see, a couple questions that you'll see on your review or on your midterms. So you do have everything you need to know, but this is a great extra lesson and there's a little extra bonus assignment that goes along with it. So just as a quick process reminder, if you need steps, I know I gave it to you as a picture last time. I've written out the steps again. So first of all, adjust all your angles to be referenced from 0. If you do that, you don't have to think about which relationships you're using for sine or cosine. Then you're going to calculate your x and y components. If you're calculating x, you'll use cosine, y, you'll use sine. It's all based on what x and y would be if we were in the first quadrant, starting with drawing first x across horizontal and then up to y. You're going to calculate your x. I guess I have calculate x and y components twice. It's that important. Then you're going to sum your x and y components. So add the components together. Draw the vector addition with the sum x, y components. Calculate the resultant magnitude using Pythagorean theorem, and then calculate the resultant direction using tan. You're always going to use tan for finding your final direction. I'll take out that extra number 3, but that gives you 6 quick steps, and they're pretty quick steps, to calculate a vector addition. All right, so what do we do when we sum 3 vectors? I'm just going to hide this thumbnail video because I want you to be able to see all of the information. So it says, find the sum of the following 3 vectors. So in this problem, this is actually a question I've used on a test before, so that can be a good little tip for you. In this particular example, we have 3 vectors. We have vector A at 60 degrees. So 60 degrees. It's 42 units long. Vector B is at 78 degrees, but not measured from 0 this time. And it is 22 units long. And then vector C is perfectly pointing south. So when it's pointing south, we could say that it's at 270 degrees. We don't have to specify how many degrees when we have it pointing south, and those are our 3 vectors. So the first thing we're going to do is calculate our x and y components. So vector A, we don't need to correct, well, I shouldn't say, let's correct our angles first. Vector A, we don't need to correct the angle, but vector B, we do. So vector B, here is 180, and I go back 78 degrees. So 180 minus 78 gives me 102 degrees. So that's our corrected angle. So let's figure out our components. So for vector A, we have 42 times the cosine of 60, and then 42 times the sine of 60. Putting those 2 in your calculator, you will find that the length vector A has an x component of 21 and a y component of 36.4. Vector B, 22 units long times the cosine of the corrected angle, which is 102, and then 22 times the sine of the corrected angle. Get my numbers in there right. Doing those in your calculator, you will get a negative 4.6, which if we look here, it's pointing in the negative x, positive y direction. So that makes sense that this is giving us a negative, and 21.5 for the y. Now for vector C, we could write out our sine and our cosine, but just let's think logically for a second. It is resting directly on the y-axis. So at this point, this is an x equals 0 point right here. So since it's lying on there, it has no x component because it's perfectly vertical, and it has a y component equal to the length of the vector of 37.0. Now you could verify that if you wanted to verify it, all you'd have to do is in your calculator, put in 37 times the cosine of 270, and you will get 0 degrees anyway. So anytime a vector is lying directly on an axis, it can be represented with just one component. So anytime you have a component that's equal to 0, it's like saying that vector is just y, it doesn't have an x piece to it. All right, so let's figure out the sums. 21 minus 4.6 plus 0 gives us 16.4. I didn't put units in these, unfortunately. So 16.4, and then here 36.4 plus 21.5. Oops, that should be a negative 37. This is downward. Minus 37 gives us 20.9. So now what we want to do is we're going to draw our new triangle. So I always draw x first. So that's our 16.4. Then we draw our y vector, and it's positive, so it's upwards, 20.9, and our resultant. Now we need to calculate the resultant and the angle. You'll notice we're in the first quadrant, so we will not need to correct the angle. You can tell that just by looking at it without doing anything else. So we're in the first quadrant. This line measures from the 0 line, so no correction is required. So we want to find the magnitude. R squared is going to be equal to 16.4 squared plus 20.9 squared. Adding those together, R squared is equal to 705. Whoops, getting ahead of myself, 7. Take the square root of both sides, because we want just R, and we find the resultant length is 26.6. All right, so that's our length. Then we want to find the angle. Well, we know we use tan, so the tan of the angle is equal to opposite, which is 20.9, over adjacent, which is 16.4. Now you could remember these as y on top, x on the bottom. I tend not to like to remember it that way, just in case you've drawn the triangle wrong. Like if for some reason you drew the triangle going upwards first, upwards, the y first, and then go across, the opposite and adjacent are going to change. So I still like to go back to which one's opposite, which one's adjacent, rather than memorizing a rule for tan. It solves a lot of the little mistakes that I see on assignments in this section. So our angle is equal to 52 degrees. Now I'm assuming you know how to do this part. So you find your decimal and then the inverse tan of it. If you can't get that 52 degrees, go back and check your trig lesson. Okay, so we know the length is 26.6. The angle is 52, so the sum vector for our final answer is going to be 26.6 at 52 degrees. And that 52 degrees is from 0. Okay, so we could actually draw that into our diagram if we wanted, but we don't need to. All right, one more example, and that's all I'm going to give you for these. So this actually comes from a diagram I borrowed from an electrical book. So, and the question gives us an applied question to an electrical context. Now, I know you don't understand the theory of what happens right now, but that's okay. You're going to get that next semester, and you're going to know the math that goes behind it before you learn the theory. So I'm going to give you a little bit. So three-phase systems, that's our electricity coming into our houses. Lots of things use three wires bringing electricity into things. So you have a three-phase system there, and what happens is, depending on what's on those three wires, those three phases, it causes currents to either lead or to lag. They adjust, the current changes on each wire. And what that results in is it can result in a current left over on the neutral wire. Now I'm going to let Andy deal with all the nerdy electrical stuff because I really don't have a whole lot of background in this part. But what we're going to figure out is we're going to say, okay, in a three-phase system, the neutral wire carries a current equal to the sum of the individual currents. So we're going to figure out what is the current on the neutral wire. So we want to figure out what's, after we've added maybe a motor on B and something else on C, what's the sum of the current? Now you have a perfectly balanced system if the sum happens to be 0, but in this case we don't have a balanced system. So this is the kind of math you're going to do with Andy, is you're going to have 3 electrical phases and you're going to figure out, well, what's the resultant? And these are typical numbers of degrees that you would have for your different phases. All right, so we're going to start out. So we have vector A. Vector B, vector A, let's label them, is 15 amps. Vector B is 25 amps, and it's at 120 degrees. Vector C is 20 amps, 20 amps, and it's at 120 plus 120 at 240 degrees. All right, so in order to add them together to figure out what's our neutral current, we just need to plug into our chart. So for vector A, you'll notice 15 amps lies directly on the x-axis. So if we put a little crosshair in here, this would be on the x-axis. So because it's on the x-axis and it's not pointing in the vertical direction at all, vector A is 100% x component and no y. So 15 amps for x and 0 for y. For vector B, we're going to calculate. So 25 cos 120 gives us negative 12.5. 25 sine 120 leaves us with 21.7. Vector C, we have 20 amps, and it's at 240. That gives us negative 10. And then we have 25 sine 240 for the y, and that gives us negative 17.3. Adding those together, so our sum in the x component, 15 minus 12.5 minus 10, leaves us with negative 7.5 amps. Here, 21.7 minus 17.3 leaves us with 4.4 amps. And now we're back at the same old thing that we had before. So in the x direction, we go negative 7.5. Then we're going to go upwards, 4.4. And there's our resultant, and there's our angle. Okay? So now that we have that, the resultant is equal to 4.4 squared plus negative 7.5 squared. Our resultant squared is equal to 75.61. I don't know if this is lagging on the recording or not, but I'm not going to re-record this. If it is, I apologize. All right, taking the square root of both sides, R is equal to 8.7 amps. So there's our magnitude. Now we need direction. Tan of the angle is equal to opposite 4.4 over negative 7.5. The angle is equal to negative 30 degrees. Well, when you see a negative 30, you always know you have to do a correction. So negative 30, what does that mean? Well, what that means is we were at 180 and we're going negative 30, we're going back 30. So correction is 180 minus 30 degrees. equals 150. Okay, so the sum factor is equal to 8.7 at 150 degrees. So they're not really complicated. It's just a whole bunch of little steps that you need to go through. But once you do 2 or 3 of them, it's not usually too difficult in order to solve. So hopefully that helps you out if you're doing a 3-phase system, or if you're wondering about one of those questions that asks what's a vector that has only one component? There's a perfect example. Vector A is a perfect example of a vector with one component in this one. And here vector C is a vector that only has one component. So that gives you a couple extra practice problems, and hopefully that has you in a good position for doing your exam.